Okay, the recording is starting. So from this point on, the meeting will be recorded. Luisa, I think you can start.
Okay. Okay, good afternoon, everybody. Welcome to this TMS seminar. Today, a PhD student of the Department of Physical and Chemical Science of our university will talk us about the meaning of being an organic chemistry. So, an organic chemist. So, besides mixing reagents, what does it mean to be an organic chemist? So, please, Vincenzo, will listen. I want to tell you that after the seminar, I won't be here to guide the discussion, so Marco will do it. So, please, Vincenzo.
Thanks, Luisa, for the introduction, and good afternoon, everybody. Today, first of all, I would like to thank the TMS committee for inviting me today to speak a little bit about organic chemistry and what an organic chemist does. Do not worry, this won't be a theoretical lecture about organic chemistry, and at least I hope it won't be so boring for you. But after having remind a little bit what is organic chemistry, we will see mostly what an organic chemist does as at a practical point of view, and especially what are the directions that organic chemistry is undertaking in the research in these current decades, through some examples of what I do as a PhD student. So I hope that at least you all have some basic knowledge of organic chemistry, but just to remind, organic chemistry is the field of chemistry that studies organic compounds, that are the compounds mostly made up of carbon. It originally began as the study of the chemistry of life, but even if in recent years the field has diverged a little bit from the pure study of chemistry of life, it always bears in mind what nature does and how our body functions, because as you may know, all the molecules that are in our bodies, all the reactions that take place in our bodies are can be considered organic chemical reactions. And just as a support of this hypothesis, I reported, as you can see in this slide, some examples of organic molecules that play a crucial role in our bodies. In the upper part of the slide, you can see retinal, which is involved in eyesight, ATP in the middle that for sure does not need any introduction, and in the below at the bottom of the image you can find serotonin and norepinephrine that are two important neurotransmitters. So it's true that organic chemistry is very important to better understand how we function as human beings. And the research in organic chemistry has been very important in helping us better understanding nature and universe. When performing research in organic chemistry, two main questions can be answered. These two main questions are the center of the research in organic chemistry. The first one is, how do molecules react? How do they react, with which mechanism? And this is mostly done by this type of question is mostly answered by research groups using both experimental methods, but especially using computer simulations that have gained a lot of importance in the depicting of the mechanism of reaction. The other main question that can be answered, and it's the question that I pose myself every day when working, is how can we synthesize a certain molecule? This is something that synthetic organic chemists do, and we are able, thanks to the advantages of organic chemistry, we are able to design multiple different synthetic strategies to obtain the same molecule. And we are also able, as organic chemists, to choose which synthetic sequence is the most useful one, is the best one, thanks to some parameters that we use. For ages, especially in the past, one of the most important parameter that was taken into consideration was the yield. For those who do not know what yield is, the yield of a reaction is a parameter that takes into account the amount of product obtained thanks to the reaction in comparison to the amount of reagents used. So for ages, the only way to determine if a reaction was efficient or not was in regarding how much the quantity of reagent of products that we obtained. Of course, and this is something that has gained a lot of attention, especially in recent years. It is very important not only the quantity of what we obtain, but also how we obtain it. In fact, especially in media and society, the term of chemistry and chemical has gained a negative meaning. Something that's chemical is something that's toxic or poisoning or polluting for environment. This is not true. As scientists, we have to make the people and society understand that chemistry is not necessarily a synonym of toxicity or negativity. What is important is how we do chemistry. There is a positive way to do it or a negative way to do it. And in last years, especially in organic chemistry, we are trying to make a lot of efforts to perform a positive way of positive organic chemistry. Something that has been of great help in doing so have been the 12 principles of green chemistry, introduced more than 20 years ago by Anastas and Werner. This can be considered mostly as guidelines that chemists can follow when they want to ameliorate, to improve the sustainability of a chemical process. These 12 principles are transversal, so they can be applied in all fields of chemistry, but in organic chemistry, especially, they have been applied a lot in organic chemistry, especially because organic chemistry has been considered as the most polluting one. I won't go through all of them. As you may see from this picture, there are several strategies, say for the use of safer chemicals that are not toxic for human and for environment. The use of strategies such as catalysis that can improve the sustainability and so on. We will see again these 12 principles later during the presentation, and how they can be implemented in organic synthesis. Just before going any further, I would like to explain to you a little bit what we practically do as a synthetic organic chemist. As I may imagine, the vast majority of us think about organic chemistry as something that's really theoretical, reactions that has to be written on paper or in a book. In reality, those reactions that we write on paper can be practically made in labs, and the practical part in organic chemistry is very, very important. So let's go through the steps that can be followed when performing a synthetic synthesis, an organic synthesis on lab. For sure, the first point and the most important part is the planning and the design of the synthetic strategy on paper. This is very important, and this can be and is mostly done by using literature sources, so the researches that have been done by others before us. When planning a reaction, two main approaches can be followed, and that I like to call reagent-based and product-based. The reagent-based approach is the one that's most used in laboratory, so in basic research, and it is useful to test the reactivity of some known reagents, some molecules. When using this approach, we are not interested much in what we obtain. We are interested in the fact that at least we obtain something from our reagent and from testing our reagent in that particular reaction condition. The other strategy that is product-based, on the contrary, is based on the fact that we want to obtain a particular type of molecule B, of product B, because this molecule has some interesting, may have some interesting properties, and so we plan always, usually thanks to a strategy that's called retrosynthetic analysis, we plan the pathway to synthesize it. And as you may imagine, this is a strategy that's mostly used in industry or in laboratories that work on applied organic chemistry. So they study the real application of our molecules. So after having planned a reaction on paper, we have to move on to practice, remembering that what perfectly works on paper does not always work so perfectly in practice. And so we mix and we weigh and mix all the components that we have chosen to use. Is usually in general using this type of furniture that are round bottom flask, in which we introduce our reagents and a solvent. A solvent is a chemical compound that is inert, so it does not react with our reagents, but is only used to create an homogeneous environment. To further increase the homogeneity of our reaction mixture, we usually use magnetic stirring. So we put this little bar that under a magnetic field keep the solution or our mixture under stirring, and then we perform our reaction at the appropriate temperature. That means that we can perform our reaction at room temperature, or at we can heat the reaction, so performing it above room temperature, or below it by refrigerating it. How to choose at which temperature perform a reaction? This is something that's mostly done by using the literature references. It's something that's that has already been done on similar reactions. In general, we heat a reaction when we want to speed it up, because heating is a way to accelerating a chemical reaction. On the contrary, if the reaction is very rapid, or if it's quite exergonic, so it generates amounts of energy, we refrigerate it to slow it down and to make it more selective. And then we perform the reaction for a recommended amount of time. This is something that cannot be determined a priori, because even if we have a similar reaction that has already been done, we could only have a suggestion on the possible amount of time needed. A way to behave is to monitor, to control step by step the reaction, to see when the reaction is completed. This can be done using different strategies. The most used one is to control the disappearance of the reagents, because as you may easily understand, when we have no more reagents in the reaction mixture, this means that the reaction is completed. And we can monitor the consumption of reagents using different techniques. Some of them are very it needs the use of instrumentation, but one of the most used one, because it's very simple and easy, is by using TLC plates, like the one I reported here in the slide. A TLC plate is basically a plate covered with silica, and it is based on the principle that different molecules with different structure migrates differently on silica gel. So what we do is to spot on these plates the pure reagents we are using and our reaction mixture. As you can see in this image, the S was the first spot. S is the reagent, and the second spot, A, is the reaction mixture. And then we elute the TLC using organic solvents. This, as you may easily understand, this is something really easy to understand visually by comparing the position of the spots. As we can see in A, that is our reaction mixture, there is no more the spot that corresponds to our reagent, so it means that our reagent has been completely consumed, and so the reaction is ended. Of course, this is sometimes we cannot easily understand this by performing simple TLC analysis, so we have to use more complex instrumental techniques, but this is something that in general is quite useful. After having seen that our reaction is completed, what we have to do is to isolate our product. Or in this case, the product is only one, but it can happen when performing reactions mixture that we have several different spots, several different products. So we have to isolate the product that we need, and we have to purify it. The purification can be done using different techniques. One of the most used one are the one that I reported here, liquid-liquid phase extraction, that helps us to separate our product from all the impurities with different polarity, or column chromatography, that's based on the same principle of TLC, so on the different rate of migration of the different compounds on silica gel. And but other techniques can be used, distillation, recrystallization, according on the physicochemical properties of our compound. After having purified our product, we have to be sure that the product we have obtained is the one we needed when we are performing synthesis according to the product-based approach. And how to do so? We have basically to create the ID card of our product. to be sure that the structure we have obtained is the same we wanted. And we do so by collecting some spectra, thanks to techniques such as NMR, or ER spectroscopy or mass spectroscopy. These are the spectra can be easily analyzed because the peaks, the signals you see are obtained with a rationale, not randomly. And so thanks to this analysis, to the analysis of this spectra, we are able to understand the structure we have obtained. And if we have obtained the one we wanted, well done. On the contrary, we have to go back to point 1 and to repeat all these steps we have gone through in these slides. Of course, as I said before, the molecule we have obtained can be used in everyday life because it can have some interesting applications. Here I reported some of the most known applications of organic compounds in everyday life. For sure, the most famous is the use of organic molecules as drugs. It is true that, especially in recent years, biotechnological molecules such as proteins or monoclonal antibodies are gaining a lot of interest in the field of therapy and drugs, but nowadays in the vast majority of drugs in market are still organic molecules obtained with organic synthesis. As I said, perfumes, polymers, by far the organic chemistry has been very important in developing all the polymers we used, and also dyes, both for visible light, but also fluorescent dyes that are very useful to mark and to dye selectively, for example, cells or components of cells. As I said before, so this has been just a journey through what we practically do as organic chemists. Of course, this is mostly based on my experience as a synthetic chemist. There are other fields in organic chemistry, other type of work that can be done differently. But in general, when performing a reaction, a synthesis, these are the steps that have to be followed. And now I wanted to show to you some examples of what I do as an organic chemist, to show to you that organic chemistry is not something only book-based, but it's something that's even ever growing. So it's a field very with a fast growing, and especially what I do as a PhD student is to find sustainable ways to synthesize molecules. So what I use as line guides are the 12 principles of green chemistry. Let's see the first example. So one way to improve the sustainability of an organic reaction is the use of one-pot multiple bond forming reactions. So imagine that we want to synthesize the molecule ABC starting from the three reagents A, B, and C. To do so, we have to create two bonds. In the traditional way, the way that has been used traditionally in the past to synthesize molecules, organic molecules, we were able to create one bond per step. So if we wanted to create two bonds, we had to make two steps. So react firstly A and B, isolating the intermediate AB, and then reacting it with C to obtain the molecule we wanted. Of course, this is a strategy that's quite time consuming. It's long. Of course, in this case, we had only to generate, in this example, we had only to generate two bonds, so we had only two steps. But we have to imagine that the molecules that are synthesized nowadays in organic chemistry are very complex in structure. Most of the time, the bonds that have to be created are more than six, seven. So we have to make, we will have very long synthetic strategies. And the main drawback of this traditional way of performing synthesis is that we have to isolate each intermediate and to purify it. The purification, as we saw, is very time consuming, but the main disadvantage is that it is the step during organic synthesis where the major amount of wastes are produced, and so these wastes that can be also very toxic for human and environment are that have to be are very difficult to treat, may be very difficult to treat. So we had to find some strategies that enable us to shorten this synthetic strategy and to reduce the amount of waste produced. And one of these strategies is, of course, the one-pot reactions. One-pot reactions are reactions in which all the multiple bonds, so 2, 3, 4 bonds, are generated at the same time in just one step. This is something, of course, really very interesting in considering the 12th principle of clean chemistry, because we are reducing because of course we are having a high atom economy and step economy. We are reducing the length of the synthetic strategy with an important reduction of the cost of it. And also we are reducing the derivatives and the waste is produced, because as we said, we are concentrating, we are shrinking several steps in just one or two or few synthetic pathways. But there is also an important energy efficiency, so an important energy consumption reduction, because imagine if we have to heat to promote the reaction. Of course, heating for 6 times is much more consuming than eating for just 1 time. So this is one of the strategies that's very used nowadays, and we use this strategy of one-pot multiple bond forming reactions to synthesize these molecules that are nitrogenated heterocycles. Nitrogenated heterocycles are very important because they are widespread in nature, so they are very useful for their biological properties. But they are quite difficult to obtain. Their synthesis is quite demanding because they are aromatic in structure, so quite difficult to be synthesized. In the past, the synthesis of these compounds were made using very harsh conditions, so high temperature, chemicals that may be very toxic. So in a way to improve the synthesis, to make the synthesis of this compound more sustainable, we designed and synthesized these reagents that's called INON. That's perfect for one-pot reactions, because INON, as you can see, bears multiple different functionalities with different chemical reactivity. In this case, we have an amino group, a triple bond, a ketone group. And so this molecule summarizes in itself different type of reactivity. So it is the perfect platform to perform this multiple reaction. And we reacted these INONs with carbonyl compounds in ethanol. As you may imagine, ethanol is an organic solvent, but it's for sure very biocompatible, and so it's greener than most of the solvents used in organic chemistry. What we interestingly noted is that by keeping the reaction conditions unalterated, so the same, but changing the other reactant, the carbonyl compound, we were able to obtain different structures by creating an increasing amount of bonds. So as you can see, from using cyclic ketones, we were able to create 2 new bonds. The new bonds are highlighted in red. Using beta ketoesters, we were able to generate 3 new bonds. And at the end, when using ketones, we were able to obtain 4 new bonds. So these strategies are very useful as multi-bond forming reaction. But the most important thing that I want to highlight is that by changing only one condition, so the carbonyl compound, we were able to obtain different molecules that are, of course, are similar because they are the same. They have the same core, the nitrogenated heterocycle structure, but have different appendages, have different substituents, and this is something very useful, for example, when synthesizing chemical libraries for medicinal chemistry purpose, so to test this compound as potential drugs, because it has been demonstrated that it's in the interaction of this molecule with the biological target, the most important part is not the core, the common core, but it is the appendages, and so having a chemical library that's very diverse in appendages is quite very useful. Another strategy, another example, is the use of safer solvents to perform organic reactions. As I said before, we tend to always use safe solvents. For example, ethanol was a much safer solvent than the most used in organic, the majority of the solvents used in organic chemistry. But by far, water is one of the most safe solvent and most green solvent that can be used. Water, in fact, is non-toxic. Is biocompatible because it is the solvent in which the reactions in our body take place. It's non-polluting, so it's compatible with the environment, and it has also some interesting chemical physical properties when using it as solvents, for example, the high boiling point. However, water has some major drawbacks when used as solvent in organic chemistry. It can interact with some functional groups, and so some types of reactions cannot be performed in water. But the major drawback, the most important drawback, is that water is a polar solvent. On the contrary, organic molecules are, for the vast majorities, in the vast majority of cases, apolar, so water is not able to solubilize them. And as we saw, as we said at the beginning of this presentation, the use of solvent is very important to create an homogeneous environment for our reaction. If water is not able to solubilize our reactants, the reaction cannot be cannot be reproducible, and we may have some problems when performing it. So for decades, the researchers that have been involved in the use of water as solvent for organic chemistry have tried to find some strategies to improve the solubility of organic compounds. But it has also been demonstrated that homogeneity is not always needed, is not always important, because it has been demonstrated that in some cases, when performing the reaction without solubilizing the reagents in water, the reactions experienced an enhancement of rate in comparison with the same reaction but performed in organic solvent. And this is something that we have tested. As you see, we chose a reaction that has already been performed using dioxane. That is a solvent, an organic solvent that's used that's used a lot in organic chemistry because it has the capability to solubilize to the vast majority of organic compounds, but it can be, of course, quite toxic. And we performed the same reaction. I won't go through much on the details of this reaction. What I want to stress is the fact that we performed the same reaction on water, just making some little changes on the reaction conditions. And although we obtained a lower yield, the reaction is possible, and most interestingly, it needs a comparable amount of time of the one done in dioxane, but at room temperature. So without heating, and as we said before, heating is a way to speed up a reaction. The fact that the reaction can be performed at room temperature is very important on a sustainability point of view, because as we said, heating requires energy, and the energy consumption, the reduction of the consumption of energy, is one of the 12 principles of green chemistry, so it's very important to perform it. to be able to do a reaction at room temperature. The meaning, the reason for this rate enhancement has been described, has been attributed to different type of factors, but the main use effect to explain this rate enhancement is the on-water effect. So we have to imagine that when performing our reaction, organic reaction in water, we have that biphasic mixture, in the sense that our organic molecules that are apolar do not solubilize in water. On the contrary, they tend to escape from water. They tend to aggregate, to concentrate, to come together, to reduce at minimum the interactions with water that are non-favorable interactions. Because of this disaggregation, we can find in our reaction mixture areas of hyperconcentration, areas in which the concentration, of our reagent is very, very high. And as you may remember from general chemistry, the speed, the rate of a reaction is a function of the concentration of reagent. So being able to create areas of high concentration is probably the reason why we are able to improve so dramatically the rate of our reactions. And in my opinion, this is the most important part in using water, the most important advantage in using water as solvent, because it enables to, as I said, to perform the reaction even at room temperature at in short amount of times. It's true that water can be considered as a green solvent, but the advantages of using water instead of organic solvents is more pronounced when using when performing reactions on a great scale, for example in industry, because this avoids the use of large amounts of organic solvents that are also quite difficult to handle because of their flammability and because of their toxicity. On the contrary, on a laboratory point of view, where very small amounts of solvents are used, the use of water instead of organic solvents is not so advantageous. The most advantageous thing is that we are able to perform the reaction at a much needing a very reduced time. So this is it. I hope that thanks to this presentation, I have been able to show to you that in reality organic chemistry, it's something that permeates our life, everyday life. It's something very important that can really truly help us understand how we behave, and that it's something that it's trying to change the situation that probably chemistry has caused since now. So thank you for your attention and time.
Okay, thank you, Vincenzo, for your nice presentation. So we have one question from Professor Teti. Maybe I missed it. I missed if the product you obtain is the only one expected, or if you have to purify it from a number of different products randomly obtained.
Yeah. Of course. That was the one example. The example that I reported in the slide was just an easy example to make you understand how we how a TLC determination works. This would be the most. It would be very great if we would be able to obtain a single product from a single reagent. Of course, in the vast majority of cases, when performing chemical reactions, several byproducts can form together with the one we need. So we have to purify and isolate the product we want. If the product we are synthesizing, it's something that has already been discovered, we can easily understand also by TLC or other instrumental techniques which is the product we want, and so the purification is is way simpler. When, on the contrary, performing a reaction for the first time, so for example, on a reagent-based approach, of course, we do not know the identity of all the spots we obtain, on all the spots we see on TLC, and so the purification has to be much more complex because we have to isolate each of them. So yes, it would be very great if it would be a great achievement if we would be able to create a synthetic strategy that enables to obtain a single product. But in the vast majority of cases, in the reality of cases, it is not always true.
Okay, very good. We have one more from Luisa Giansanti. Just a curiosity, some of the products you obtained showed some pharmacological activity?
Yes, so that's something we do not determine as organic chemists, because we are more interested on the test of the reactivity of organic molecules. But of course, the products we obtain may have several properties. For example, as I said, these types of molecules bearing these quinoline rings are very interesting, may have interesting biological properties. Quinolines are known to be antibiotics used as anti-cancer drugs, so they may have some interesting properties. However, we do not test them on this way because we have not the capabilities and the knowledge to do so. But we are open to collaboration. So yes, probably they could be. Of course, these molecules are not synthesized in a specific way to test for a particular property. They are obtained randomly to test the reactivity of I known that is our reagent. So probably they can have some properties that we do not know. And yes, of course, it would be great if we could be able to test them.
Yeah, if I can add one thing, I think, for example, fluoroquinolones are very active antibiotic drugs. They intercalate DNA, so I think they can be used as anti-cancer drugs as well.
Yes,
so yeah, absolutely.
Yes, of course. This is only, of course, if we if we are able to, if we find peculiar properties and we discover that some peculiar substituents are needed, we can implement the synthetic strategies we have developed to introduce these substituents. So this is something that can be done without any doubt.
Mm-hmm. Very good. So we have one more from Chiara Puri. How important is computer-aided molecular design in your work?
Yes, it's true. It's very important. In my work as an organic chemist, a synthetic organic chemist that, as I said, is mostly interested in testing the reactivity of new reagents, computer simulations using quantum theory or density functional theory are very important to better understand the reaction mechanism, how a reaction goes through. Of course, we perform some experiments, so practical practical studies to test our hypothesis, but computer simulations are very important to help us, because sometimes the mechanism is what we obtained is very unexpected. So yes, computer is very, very useful. Molecular modeling, it's lesser important in the type of work I presented, but it's very important, for example, when we want to hypothesize, for example, the interaction of our molecule with a specific biological target. So this is in general very important in organic chemistry, but important to a lesser extent for the type of work I do.
Mm-hmm. Okay, thank you. Chiara also says thank you. So I have a general question, because I know you've been in Nice for some months in France.
Yes.
So since we have a lot of people who are, you know, planning or thinking to go abroad for an experience, but you know, with this coronavirus situation, everyone is a bit
Yeah.
scared. What is your view? How useful was it for you, and do you advise people to go or not?
So the period that I spent abroad was an integral part of my PhD thesis, because maybe some of you may know, I have a PON PhD, so I was obliged to spend a period abroad. I've never been for such a long time abroad previously in my life, and so I believe that for me this experience has been really important, and really both on a formation point of view, also but on a personal point of view, also because it enables you to see another different environment of work, a different type of research. So it's also, it enables you to make connection with a new culture, a new type of way of life. So yes, I think that's very important on a personal point of, both on a personal point of view and on an educational point of view. So yes, maybe the period is not very is not so it's not so good to make such an experience, but when we will be able to travel again, yes, this is something that I will definitely advise to do.
That's very nice. Also, I'm glad we recorded this meeting, because it's I think it's very interesting for people who are choosing what to do with their lives. So you know,
Yes,
a
yes.
lot of master's degree students, or bachelor's degree students, or even people who are about to start university and don't
Yes.
know, you know, what to do in their
Yeah.
future. I think this is a very informative presentation for them.
Yes, thank you
Oh,
very
sorry,
much.
we have one more.
Okay.
Sorry, we have one more from Michela. So, Michela Ciocca, is there a branch of organic chemistry that deals with the degradation of molecules rather than synthesis? Someone who deals with generating reactions that reduce, for example, the toxicity of certain substances by degrading them? Could be useful for the elimination of toxic substances in wastewater, for example.
Yes, that's definitely the truth. There are some research groups that study this type of reactivity, the degradation of molecules. And I have to admit that I have no knowledge. I do not know if this is something that's done for environmental purposes. But as I have an as I am a medicinal chemist of formation, I know that there are some research groups that are working on studying how, for example, organic molecules used as drugs degrade in our body. So this helps to better understand, for example, the metabolites that are produced by the degradation of organic molecules by biological pathways, by biochemical pathways. And this is also very important because it helps to better understand why, for example, some drugs have a higher degree of toxicity than others. So this is something that's really, yes, this is something that's true. There are some research fields on the study of degradation. But I do have knowledge only of these studies in the field of medicinal chemistry. I do not know if the same type of studies are being done on environmental point of view. Thank you for the question.
Okay, thank you. Currently we have no other questions. If someone have one more question, they can write it in the chat. In the meantime, I can tell you about the next TMS. So the next speaker will be Gabriele Magna from the University of Tor Vergata, and he will be speaking about sensors and especially of electronic noses, which is quite an interesting concept. So make sure you're here next week. And yeah, no more questions. So I want to thank Vincenzo for being here today, and all of you for your attention. And I'll see you next week on this team. I will create the event soon. One last thing, I want to welcome. I see that there is Catherine. Katie Stoker in the audience, and she's a Manchester student who'll be here in July in our lab. So just want to welcome her and thank her for being here. So next season, I hope you'll be able to meet her in person. All right. So thank you very much, and I'll see you next week. Bye-bye.
Bye.